SN2 mechanism. Types of nucleophilic substitutions can be divided into SN2 and SN1. For SN2, it means bimolecular nucleophilic substitution. This number 2 here, bimolecular. And SN1 means unimolecular nucleophilic substitution. Why does it name bimolecular SN2? Because the reaction involves two molecules, haloalkane and nucleophile. In the rate determining step, two molecules involve, haloalkane and nucleophile. For SN1, unimolecular nucleophilic substitution, first step involves only one molecule, which is haloalkane only. We don't take account the nucleophile. We look at haloalkane only in SN1, in the rate determining step. SN2 mechanism. Primary haloalkanes undergo SN2 mechanism. So you have to look at the class of the haloalkane. Primary haloalkanes undergo SN2 mechanism. The process of bond breaking and bond forming occurs simultaneously, means at the same time. One-step mechanism, that's SN2. This occurs for primary haloalkane. This is second order kinetics because the rate we look at the concentration of haloalkane and nucleophile. So second order. It depends on haloalkane and nucleophile. Power 1, second order. So haloalkanes react with nucleophile. So this OH minus as the nucleophile replace the Cl in haloalkane, making chloride as the leaving group, chloride ion as the leaving group, and OH bonds with R group CH3. Okay, so the rate of this reaction here is K, haloalkane concentration and nucleophile concentration. We take account both. Okay, take account both. The rate depends on both concentration of haloalkane and nucleophile concentration. So that's why it SN2, bimolecular nucleophilic substitution. Two molecules involved, the haloalkane and nucleophile. It is one-step mechanism, so it occurs simultaneously. The bond breaking and bond forming occurs simultaneously. It has a transition state in the middle. No carbocation rearrangement. In SN2 mechanism, no carbocation rearrangement means there's no formation of carbocation. We start with the nucleophile attacks the carbon in the haloalkane. The carbon is delta plus. This is what we call back attack. Okay, at the front it has the halogen atom. So it attacks from the back, the opposite side of the halogen atom. Nucleophile back attack the C delta plus. Okay, use one of its lone pair to form bond with this carbon simultaneously, and this bond, 2 electrons will be given to the halogen atom. Okay, this bond breaking and bond forming transition state. So this reaction is slow reaction, and then after transition state it is fast reaction. So make sure if you want to draw SN2 mechanism, you start with this 2 solid bond. Make sure you draw 2 solid bond. You have to draw in 3D, 2 solid bond, and then this dotted line and wedge bond here. And then in the transition state, both dotted line and wedge bond is drawn like this, and nucleophile opposite side of the leaving group halogen atom over here. And then if you look at the angle of drawing at the product in the reactant, or angle, this solid line is on the left, this dotted on the left, wedge on the left, and at the product, the angle is different, the opposite. The solid line on the right side of carbon, and this dotted line on the right side, and slightly right for the wedge line. So you must show like this differently in the reactant and at the product. So from the transition state to become the product, the reaction is very fast. The leaving group, halide ion, and product, the nucleophile replace the halogen atom bonded to the carbon. So this is the product of SN2 mechanism. One step mechanism only. Okay, no carbocation involved, so no carbocation rearrangement. This is how you draw SN2 mechanism. For example, OH minus reacts with haloalkane. This OH minus is the nucleophile. It will replace the halogen atom in haloalkane, becomes alcohol and halide ion as the side product. All SN2 reactions proceed with backside attack. This is what I mean by backside attack. The nucleophile attack the carbon that is delta plus, carbon that is attached to the halogen atom. It attacks from the back. This is at the front, where the position of halogen is at the front. So this is at the back. So this is backside attack, resulting in inversion of configuration at the electrophilic carbon atom. The nucleophile approaches for the site opposite the leaving group. So opposite the leaving group is on the right, the opposite is on the left. This is what we call backside attack, or attack from the opposite of the leaving group. Okay, so this bond consists of 2 electrons transferred to the Cl atom. The reaction is slow to become a transition state. Okay, make sure you draw the bond on the left, hydrogen, hydrogen, hydrogen here on the left. Because SN2 mechanism, primary haloalkane, okay, here, or hydrogen. And then, so in the transition state, make sure you draw balance, these 2 bond, balance left and right, and then 1 hydrogen here in the middle. And then on the left, whatever attack from the back is on the left, and the leaving group on the right, and the hydrogens that you draw initially slightly tilted on the left. At the product, it must be on the opposite side because the nucleophile is inserted to this side. So that's why all other atom is pushed like this, plus the side product halide ion. So this is for SN2 mechanism for primary haloalkane. Okay, it occurs for primary haloalkane. The order of reactivity in SN2 mechanism, increasing rate of SN2 reaction. So this is the least stable tertiary. The primary haloalkane and methyl halide. Methyl halide, the most stable for methyl halide. So the example that I show here is methyl halide. Okay, if you don't have methyl halide, primary haloalkane is also occur for SN2 mechanism. The higher the number of alkyl group, the lower the rate of SN2 reaction to happen. So SN2 does not favor secondary and tertiary. Okay, least stable tertiary, most stable methyl halide. So if the haloalkane is methyl halide, then SN2 mechanism will happen for sure. The backside of electrophilic carbon atom is hindered by the presence of bulky alkyl groups. That's why it does not favor tertiary and secondary. If tertiary and secondary, here, tertiary and secondary, you have R group here, R group here, that's for secondary. If tertiary, all R group. Tertiary, all R group. So this nucleophile will be difficult to attack this carbon because you have big R group over here for tertiary. Secondary as well. If secondary, you have 2 R groups here, and it will be difficult for a nucleophile to attack this carbon delta plus. Okay, that's what we call steric hindrance or steric effect. Steric hindrance caused by bulky R groups makes nucleophilic attack from the backside more difficult and they slow the reaction rate. So nucleophile attack is possible or easy. Okay, if the R group is one R group only, it's possible or easy. But here, if it's bulky, nucleophilic attack is impossible. Okay, if it's bulky, it's impossible for nucleophilic attack from the backside. So that's why SN2 mechanism, it favors methyl halides and primary. Okay, so this is primary haloalkane, only one R group, one alkyl group attached to carbon, primary. And then this is secondary haloalkane, two alkyl group attached. Tertiary haloalkane, three alkyl group attached. So this SN2 does not favor tertiary. Okay, it does not favor tertiary because the back attack is hindered by these R groups. Okay, tertiary alkyl halides are more hindered than secondary alkyl halides. Secondary alkyl halides are more hindered than primary alkyl halides.